Okay, guys. So last time we finished chapter 1.1. So that was the limit of a function. And let's start the day by going over the homework. That was 15, 19, 21, 24, 25, 26. So let's start with number 15. So it gives us three limits for us to work with. The first one is limit x goes to infinity of 8x squared minus 3x plus 1 over 2x plus 1 squared. Okay, so do we remember how to evaluate these kinds of limits? It's an infinity over infinity, which means we got to compare the degrees of the numerator and denominator. The numerator has degree 2, denominator also has degree 2, so we just compare the ratio of the leading coefficients. So that's 8 over 2 squared, right? So that's 8 over 4, and that gives you 2, which is correct for A. So A is correct. B gives you limit x goes to infinity of 2x plus 1 over square root of x squared minus 2. So again, it's a limit. The limit is infinity over infinity. We compare the degree 1, and then the square root x squared has degree 1. So we just compare the leading coefficients 2 over 1, and that's also 2. Okay, the third one, and B is also correct, right? B is also correct. The third one, limit x goes to infinity of 3x plus 1 over square root of x squared plus 1 plus x, like that. Okay, again, plug in infinity. It's an infinity over infinity. Compare the leading coefficients. Here, we just have to be careful of not to lose the plus x over here. So it's 3 over square root of 1 is 1, plus 1, that gives you 3 over 2, which is, for C, that's incorrect, right? So your answers would be A and B. And the next one is 19. Okay. So 19, we find constant A. Find constant A so that limit x goes to infinity of square root of x squared plus ax minus square root of x squared minus ax equals 3. So if we plug it in, it's an infinity minus infinity limit. Remember, our goal was to rationalize this radical expression so we can turn the infinity minus infinity into an infinity over infinity. So we can rationalize. Multiply the conjugate, then what does the numerator become? X squared plus ax minus x squared minus ax. So let's write that out for now. Minus x squared minus ax. And then the denominator is square root of x squared plus ax plus square root of x squared minus ax. So as you can see, in the numerator, the x squares cancel out, which leaves you with x goes to infinity. We get ax plus ax, right? Ax plus ax is 2ax over square root of x squared plus ax plus square root of x squared minus ax. And then it's an infinity over infinity now. Degree 1, we compare the leading coefficients 2a over 1 plus 1, right? And that has to equal 3. So can factor that out, right? 2a over 1 plus 1, so a equals 3. So that would be your answer. Okay, the next one was 21. Okay, so this was one of the more tricky ones. So we did number 20 last time. 21 gives us a slightly different scenario from number 20, but the gist of how we solve it is pretty similar. F of x satisfies limit x goes to infinity of f of x over 2x squared plus 3x plus 5, and that has to equal 1. And limit x minus 2, x goes to 2 of x minus 2 over, under f of x, has to equal, what is it, 6? 6. And then we're asked to find f of 1. Okay, so here's a classic problem where you have to look a little bit deeper than just evaluating these with algebra. From our first limit, we notice that x goes to infinity and the denominator goes to infinity, but the limit itself goes to 1. So that means that the limit exists, right? So if we're going to compare the degree, remember f of x is a polynomial function, the degree of f of x has to be 2 in order for the limit to exist at all. If it's less than 2, the limit would be 0. If it's more than 2, the limit would be infinity, right? So f of x must have a degree of 2, and then the leading coefficient of f of x, right? We're going back for more information. 2 under something has to be 1, right? So the leading coefficient of f of x must be 2. 2x squared plus blah, blah, blah. Does that make sense? So we figured out the degree and the leading coefficient just from the first limit. Now we take a look at the second limit. X goes to 2, so the denominator goes to 0. So the numerator also has to go to 0. Why? Because the limit exists and it's not like infinity or 0 or that sort of like special number. The limit has to exist, so f of x has to go to 2 when x goes to 2. So we can figure out that f of 2 has to be 0 as well. Okay. So knowing these two pieces of information, how can we set up the expression for f of x? Well, remember that if we know a certain root, it's better to put it in its factored form, right? So we can grab the leading coefficient at the front, 2, and then we can go x minus 2 because it has a root of 0, but we don't know what the other root is yet. So we'll set that as a variable like k, something like that. And that makes it easy for us to plug back into the limit. So let's focus on the second limit and plug it back in. So x minus 2 factors this out. So the resulting limit is limit x goes to 2 of 2 times x minus k, at which point you can plug into, which is 4 minus 2k, and that has to equal 6. So 2k equals negative 2, k equals negative 1. So we found our last bit of information about f of x. So therefore, f of 1 has to equal 2 times negative 1 times x plus 1. So 2, and that would be negative 4 as our answer. Okay, does this make sense, guys? So just remember that you can get a lot of information out from just a single limit. So just don't look at it once, make sure to come back to it and see if there's any additional pieces of information that you can use, okay? All right, the next one is 24. I think that's the application problem, right? So let's do 24. So the situation here is that we have y equals square root of 2x. So we have y equals square root of 2x. And we have a point A on that curve. And then we're going to draw a perpendicular line down, and that foot is B. And then we have the origin point O. And what are we trying to find? Limit A goes to infinity of f of A. So A is A comma B, and f of A is what? OA minus OB equals OA minus OB. And we want to find limit as A goes to infinity of f of A. Okay, so OA is this line segment right here, right, guys? Yeah, and let's solve that limit. We can immediately figure out the coordinates of B, right? It's a perpendicular line down, so B is A comma 0. And we can, rewrite this as what? A comma square root of 2a, since we already know the function. So what is f of a, guys? OA is going to be, we can use Pythagoras, right? So this length is going to be a, this length is what? Square root of 2a. So OA squared equals a squared plus 2a, right, guys? So OA is positive, so we can just square root it, like that. And then how about OB? OB is just what? It's more simple. OB is just a. Therefore, we can write our limit out as a square root of a squared plus 2a minus a as a goes to infinity. So what type of limit is this, guys? It's an infinity minus infinity, right? So with infinity minus infinity, we can rationalize to make a fraction. So let's do that. A goes to infinity, a squared plus 2a minus a squared, right? So the numerator becomes 2a, and then our denominator is a squared plus 2a plus a. So that gives you an infinity over infinity. They're all degree 1, so let's do 2 over square root of 1 is just 1 plus 1, and the limit that we're looking for is 1. Okay? So that's, I think that's more simpler than what we did with number 23. All right, so the next one is 25. Now the difference between 25 and the problems that we solved before is that 25 doesn't give you an explicit variable or like an explicit limit expression. So the situation that we have going on here is that we have the equation, we have the parabola y equals x squared, and then we have point P on that parabola, and then it says this. Well, does that look more pretty? Point Q is on the y-axis, so that Q is the center of a circle that passes the origin point O and P. So I guess Q would be somewhere here, and there's like a circle that passes the origin point and P, something like that. And what's going on here is that P will get infinitesimally close to O. So it will slide down the parabola towards the origin point, and it tells us that when P is doing this, Q approaches some point on the y-axis, and we have to find that point, right? So it doesn't give us an explicit limit expression to evaluate, but we have to set up our own limit expression to solve this problem. Okay, so a couple of things to note. Remember, if you have a circle, this is going back to geometry, if you have the center and a tangent line, the angle between the tangent line and the radius to that tangent point is always going to be 90 degrees. So as you can see here, the Q is always on the y-axis. It's defined that way. And the circle passes through the origin point. So it passes through 0, 0. And the x and y-axis are, right, by definition, perpendicular to each other. That means that this circle is actually tangent to the x-axis. So we can make note of that. What property can we use about circles? Well, a circle, the distance from the origin to any point on the circle has to remain the same, right? So maybe we can use that property here. Now, Q, I think we can maybe make two variables here, right? Our goal with any like geometry or graph problem, if we don't know a lot of stuff, we try to express it with a minimum number of variables. But I think for this one, we can express it using two variables. Since I know that P is on the parabola y equals x squared, I can set P's coordinates as t comma t squared. And since Q lies somewhere along the y-axis, I'm going to say that the radius of the circle would be r. Then we automatically get Q as what? 0, r. right? And then what expression we can use is that we can find the distance between P and Q, and that also has to be R, right? So the distance between P and Q, we can use the formula, right? T minus 0 squared plus T squared minus R squared equals R squared. Okay, and should we try to expand this? Then we get T to the power 4 minus 2RT squared, and then we have plus 1, right? So plus 1 minus 2R t squared plus r squared equals r squared. Okay, so what we have here is that we can cancel out the r squared. And then, since we know that t is not going to actually be 0, right, guys? Whenever we divide or cross out stuff, we have to make sure that whatever we're crossing out is not going to equal 0. Otherwise, we might miss something, right? But we know that p is approaching 0, but it's never going to actually equal 0. So we can cross out, we can factor the t squared out. So what we have is t squared plus 1 minus 2r equals 0. And what can we say about r? Two t squared r. R squared goes away. T to the 4 times 1 minus 2, 1 minus 2r minus 2 t squared r. Yeah, so r equals t squared plus 1 divided by 2, right? Yeah, we got that. And what we're trying to find is when t approaches 0, what would r approach? Oh, turns out it's very simple. Wow, okay. So as t approaches 0, right? T approaches 0 means p is getting closer to the origin point. Then we go t squared plus 1 divided by 2. This is the value of r, right? Of course, that's corresponding to t. Yeah, so we're trying to find the limit of r as t approaches 0, right? We're trying to find the coordinate that q would approach as p would slide down this parabola. And it's very simple, right? Is this an indeterminate form? No, right? We can just plug in t equals 0 and get 1/2. And that would be the y coordinate. And find a, that's the y coordinate as q, that's the y coordinate q approaches. So your answer would be 1/2. There you go. It's quite more simple than I thought. Okay. So these are sort of like the contextual applications that you might do involving limits. So, right, my advice is that use the least number of variables you can, because who wants more variables, right? Okay. So we have to be smart about when to make new variables. But for this one, we got like a very nice relationship between our two variables. So we were able to easily solve the limit. Number 26, this is sort of like a logic question. Select all statements that are true. Number 1, if limit x goes to a exists. Okay, if limit x goes to a of f of x and limit x goes to a of g of x exist, then limit x goes to a of f of x over g of x exists. Do you think this is true? Do you think this is always true? Yeah? Okay. If you want to prove something is true, you have to make sure that every single case is accounted for. Every single possibility has to be proven true if you want a statement to be true, right? If you want to prove that a statement is false, it's relatively much more easier to do that, because if you want to prove that this statement is false, all you got to do is find one single counterexample, and then the entire statement would be blown away, right? Because one single counterexample will make this not true. So can we find a counterexample where this would not be true? Remember, if let's say that limit x goes to a f of x equals 1, and limit x goes to a g of x equals 0, right? Then what would this equal? Does not exist, right? Because the constant, remember, constant over 0 could be plus minus infinity, but either way, that limit would not exist. So number 1 is false. Number 2, if limit x goes to a f of x and limit x goes to a of f of x plus g of x both exist, then limit x goes to a of g of x exists. Would this be always true? Can we find like an obvious counterexample for this one, like we did here? Like 1 and 0 are sort of like, easy counterexamples. Not really, right? So we gotta formally make sure that this can happen. So if a limit exists, what does that mean? It converges to a real number, right? So limit x goes to a f of x exists, which means that this is part of the real number line, right? We can assign a real number to it. And this is also a real number because the limit exists. Now, you take any real number, and how do you get limit g of x? You subtract f of x from f of x plus g of x, right? So you're subtracting a real number from another real number. Guys, does subtracting a real number from another real number suddenly make a number that does not exist? No, it's always a real number. So if the limit is a real number, then the limit exists. Therefore, this is always true for any case. Number 3 is limit x goes to a of f of x and f of x g of x exists. Okay. They both exist. Will limit g of x exist? What do you think, guys? Can we find a counterexample? Well, I think a counterexample for this requires you to think a little bit beyond, like raw numbers or raw values. Remember the 7 different types of indeterminate forms that we discussed. I will erase this guy. Do you remember what the 7 different types of indeterminate forms there are when evaluating limits? Yeah, so that's, I'm going to list them in order. Yeah, that's definitely 1. Yep, that was number 7. 0 over 0, right? That's the most common thing that we've been doing. And infinity over infinity, right? And 0 times infinity, infinity to the 0, and 1 to the infinity. Okay, so like number 5, 6, 7, you probably won't see until like a full calculus course when you're familiar with exponentials. But let's take a look at number 4. 0 times infinity. I think we did an example on that. 1 over x times, what was it? 1 over x minus 1 plus 1, limit x goes to 0, right? This was like number 17 or something. This goes to infinity. You plug in 0. This goes to 0. But does the limit actually exist? Well, if we take the common denominator It's 1 plus x minus 1. So we just get x left, and then we can factor out the x, and we get negative 1, right? So 0 times infinity, the limit may or may not exist. So if this limit equals 0, and this is 0 times infinity, then the limit may exist, right? It's an indeterminate form. It may exist. But does that mean that g of x has a limit? No, because it goes to infinity, right? So this is not always true because the 0 times infinity indeterminate form exists, okay? We can provide that as a counterexample. Okay, now for the final statement, remember the squeeze theorem. It definitely looks like a squeeze theorem problem. So let's see. If f of x is sandwiched between x squared and x squared plus 2x, then we're expected to find limit x goes to infinity of f of x minus x over square root of 9x to the 4 plus 1. Okay, guys, how do we know that we can apply the squeeze theorem? We know that f of x is sandwiched between two functions, right? For all positive x, and limit x is going to infinity, so that means that we should utilize the squeeze theorem. Now, the way to utilize that is to compare the left and right functions and plug them in individually. So number 1 would be limit x goes to infinity of, we can plug in x squared instead of x, instead of f of x. So x squared minus x over square root of 9x to the power 4 plus 1. And what is that? It's a infinity over infinity, degree 2, so 1 over square root of 9, 1 over 3. Now, the right-hand side, we can substitute x squared plus 2x instead of f of x. Limit x goes to infinity of x squared plus x, right, this time, square root of 9x to the 4 plus 1, and we can also verify that degree 2, 1 over square root of 9, it's the exact same thing. Therefore, this must equal 1 over 3 since the left and right sides of the limit are the same. Okay? So that was the full workbook for chapter 1. Cool. So today we're starting chapter 1-2, which is the continuity of a function. So continuity builds on limits. So we talked about like left-hand limits, right-hand limits. So let's talk about continuity. Okay. Let me tell you the definition of continuity first, okay? So 1, 2. What does it mean that a function is continuous? At x equals a, at a certain point. Now, do you guys remember the 3 conditions for a limit to exist?
X has to approach a from the right.
You compare the right-hand limit. Right-hand limit has to exist. Left-hand limit has to exist, and they have to equal each other, right? Similarly, there has to be 3 conditions for a function to be considered continuous at x equals a. Number 1, limit x goes to a of f of x must exist. Exists. Number 2, f of a must exist. Number 3, guess what? They have to equal each other. So limit x goes to a, f of x equals f of a. These 3 conditions define that a function is continuous at x equals a. So when you think of the word continuous, what do you think of? You think of like smooth curves, right? And in a way, yeah, it is. So any function that satisfies these three conditions will be continuous at x equals a. And let's take a few examples here. Okay, so let's see if the following scenarios is the function continuous. Number one, let's say that I have this curve, and then I have it like that. Okay. Now, is this function continuous at x equals a? No, why not?
because limit f of x is not equal.
Yeah, so number one, does the limit even exist for this one? Right? The left-hand limit is down here, the right-hand limit is up here, so it doesn't even satisfy condition number one. We call this type of not, when we say that something is not continuous at this point, we actually have a name for it. Guess what? Discontinuity. So there's different types of discontinuities, and based on, your teacher might touch on this. Most exams, I believe, do ask you to memorize these types. So I'll just give you the name of this. This is called a jump discontinuity. Okay? You see why? Because the function jumps. So the reason why this is not continuous is because limit x goes to a of f of x does not exist. Okay? This is the reason why. Okay, now let's go to the next scenario. How about I have a function, but it's like that. Is this continuous at x equals a? So number one, does the limit exist?
Yes.
Yeah, because the left-hand side and the right-hand side all converge to the same thing. So the limit exists. Does the function value exist?
No.
No, because it's an open hole and there's no closed holes, right? Which means that the function itself is undefined just at this point. So this means f of a does not exist. That's the reason why. Now, we call this a removable discontinuity. Okay, how about this guy? We do a similar thing, but I redefine the function, I don't know, like here. Is this continuous or not? No. Does the limit exist? Yes, right? It's here. Does the function value exist? Yeah, it's here.
Yep.
But does the limit equal the function value?
No.
No. So the limit does not equal the function value. Oh, f of x does not equal to f of a. So this is the reason why. And this is another example of a removable discontinuity. So you just remove the single point of a function. You either remove it entirely or you redefine it somewhere else.
Does there always
Yeah.
have to be a value that equals a?
So what we're doing here is that we're evaluating the continuity at x equals a. So we're just evaluating this single point.
No, I mean,
Yeah.
like, can there be an example where there's no solid point at all?
There's no solid point at all,
Yeah.
like this one.
Yes.
Yeah.
So there's just no value.
Yeah. Do you want me to show you an example? Yeah, sure. Yeah, this is a great example. Okay. How do you think these two are different? Are they different at all? No, why? Why? Because we can cross this out, right? But what did I tell you about crossing stuff out? You have to make sure that it does not equal 0 before you cross it out, right? So look at this. Y equals x is going to be this line, right? It's defined nicely at every single point. It's fine, right? But this one, we can't cross it out immediately. And that's what people miss, is that we have to be careful that when we're crossing stuff out, it's not equal to 0. When this is not equal to 0, then of course we can cancel it out, right? What does canceling out mean? We divide both sides by the same thing, right? We divide both sides by x. If x is not 0, then sure, we can divide it whatever way we want. But if x equals 0, can we divide by 0? No. That means that we can't cancel it out. And what's 0? Like, the denominator is 0, right? So we're not taking a limit here. We're literally plugging in 0, right? So if the denominator is 0, is this number defined?
Yeah.
It's not defined. So it's undefined just at x equals 0, but it's defined everywhere else. Everywhere else, it follows the same straight line, but at x equals 0, it's an open hole. It's not defined just at that point, okay? Yeah, so these are examples of like removable discontinuities. If you're looking at rational functions with like, if the numerator is a quadratic function, but the denominator is like a linear function, then you might also see these types of discontinuities.
And then I have one more question.
Yeah.
When you're defining a limit, so if there's let's say there's a graph and there's a
Yeah.
line,
There's a,
and it
yeah,
stops at a certain point, let's say at x equals 3, it just stops.
just
But
stops.
it's not continuing, or there's nothing that's
Yeah.
connecting to it coming
Yeah.
from the left. Does that limit still exist?
Does that limit still exist?
Or sorry, coming from the right, yeah. There's like no line.
There's no line here.
Yes.
Um, no, because the three conditions for a limit to exist is that left-hand limit has to exist, right-hand limit has to exist, right?
Yes.
And they have to equal each other. But if the function is somehow undefined for this region entirely, then there is no right-hand limit. It does not exist.
Oh, okay.
So the limit at this point does not exist. I can say that the limit x goes to, if this is like a minus does exist, right? Because we're only looking at the left-hand side. But the limit of x goes to a will not exist because there's nothing over here.
Is
Yeah.
that x goes to a pod plus?
Yeah, that also doesn't exist, right? Yeah.
Yes.
So the final type of discontinuity that we're going to talk about is, let's say, if I have a function like that, where the y-axis is like an asymptote. I'll just erase this example here. Is the function continuous at x equals 0 for that one? No, why not? Because the limit, of course, does not exist, right? But remember, what's different between this jump discontinuity and this one is that this one goes to infinity and has an asymptote, right? So we can say that this is called an essential discontinuity, or sometimes an infinite discontinuity, okay? So I think these are the three main types to remember and three main things to look out for when you're considering the potential points of discontinuity, okay? Ironically, right, we're more interested about discontinuity than continuity because these cases are where very interesting things can happen. So we tend to, in actual problem solving, we tend to focus more on which points on the function have the potential to be discontinuous, and we analyze them. Okay, so now let's just step away from continuity for a second, for just a second. And I want to talk about some other math concepts that is very helpful for calculus. I'm going to talk to you about intervals and sets today. Intervals and sets. Okay, so have you guys seen interval notation at all?
Is it similar to piecewise?
Like, do you know what this means?
I've seen it.
You've seen it before. Okay, so let me introduce you to this formally. Yeah. So this is a great piece of information to know, both in calculus and in parts of math outside of calculus. Intervals. Okay, so let's go back to the number line. And let's say this number line represents the variable x. And I have a over here and b over here, and I want to represent this range, right? Normally we would write what? X is greater or equal to a, and then x is less than b. We would write it like this, right? Well, there's even a simpler way to notate this, and that's where we use intervals. Now, you see this closed hole? That means A is part of that range, and B is not. We use square brackets to represent the equals sign, and then circular brackets, so like parentheses, to represent an inequality symbol that does not contain an equal sign. So we can represent this interval by writing a comma b like that, and then using these bracket symbols. Okay, so let's practice a little bit more. How about they're both open holes? Yeah, so a comma b, but with parentheses, round brackets on both sides. And this would be what? X is greater than a and less than b. How about, let's say, open on this side and closed on this side? Then we would do what? A comma b, like that, right? And closed on both sides would be both in square brackets. Now, we have a special name for this. It's called an open interval, when both sides are open. And this is called a closed interval, when both sides are closed, like that. Okay, there's two special cases. What if you wanted something unbounded? Like I start here and then I go all the way to infinity. How would we notate that? Let's, yeah, right? Square bracket a, comma, infinity. We can write infinity, but remember that infinity always has to go with a open bracket, so like a round bracket, okay? Infinity always needs the parentheses. Okay, how about if we want to represent the set of all real numbers, how would we do that? Yeah, open, and then we go from negative infinity to infinity. So that would be the set of all real numbers. Does that make sense? Okay, so it's important for us to know intervals because that's a key part of the language that you will see throughout in calculus. So let's see. Let's talk about continuity on an interval then, okay? Where should I write this? I'm going to erase this. So remember, removable can also be a case where it's like that as well, okay? And then I'm going to start, how do we define continuity on an interval? So remember, we defined continuity at a single point, right? So these are the three conditions for a continuity at a single point. But what about if I want to analyze the continuity on an interval? On an interval, then we have to look at all points in that interval. Okay, so if I want to say that this function is continuous on all points in this particular interval, then for all points inside that interval, these conditions must hold. So let's say I want to prove the continuity on an open interval. I can casually notate the interval that I want by putting the round bracket here and the closed bracket here. Okay. If I want to prove that f of x is continuous from here to here, I need to look at every single point between these intervals and make sure that they all obey those three rules. Okay. Now you asked something similar. If we're looking at a closed interval, right? Now, for an open interval, this won't be a problem because we can both look at both the left and right hand value limits. But on a closed interval, hey, if the function just stops here, then can we say that it's continuous? No, the limit doesn't exist, but there's an exception for this. So continuity on a closed interval works like this, okay? Let's say alpha, beta, closed. Number one, we have to make sure that the function is continuous on the open interval. So we have to verify that first. And then for each of the endpoints, we only have to look at their respective limits within the interval. So for beta, we can say that limit x goes to beta minus of f of x has to equal f of beta. So it's kind of being more relaxed on the rules compared to that, right? We only have to look at the left-hand limit for continuity on an interval. Number three, for alpha, if I actually want this to be also closed, we only have to look at the plus limit. So x goes to alpha plus of f of x has to equal f of alpha. So this is the only exception when we're doing continuity on an interval, is just be careful on closed intervals. You don't have to look at the both sides of the limit. Okay, so I'm going to give you a list of continuous functions, so you don't have to actually go through all of it. So list of continuous functions. Number one, all polynomial functions are continuous on the set of all real numbers. Number two, rational functions are continuous, except for when the denominator equals 0. G equals 0. What else? All radical functions are continuous in their domain. So like square root of function f of x. Exponential and logarithmic functions are also continuous, but we won't, touch too much on that in this course. Okay, so when we're dealing with polynomial functions, you can be rest assured that yes, it is a smooth continuous curve everywhere. Okay, now what I want to talk to you now is also a little side note. We're doing a lot of side notes today, but I think it's important when you're building your math skills. It's important to know different, aspects of math. We're going to talk about sets. So let's just turn to this board. So I'm going to erase, can I erase this, the interval? So sets are I think it's a very key element, even in high school math. We use them knowingly or not, because when we first learned functions, I talked about functions 2 classes ago in the last class. Um, a function is basically a relationship that maps a set to another set. So what the hell is a set? Well, a set in math, it's a group of things. Now, in theory, you could have, anything in a set, but for our purposes, most of the sets that we'll deal with are sets of numbers, whether they're, um, we learned about like the real number line. So here's how you basically define a set, basic notation. Okay, so these are extra notes. I didn't make notes for this one, but basic notation. Sets are usually denoted as capital letters. So I'm going to make a set A equals, I'm going to use curly brackets to enclose my elements. So this is the set. We have set A, and then my elements are, I don't know, 1, 2, and 3, and then I'll close the bracket, the curly bracket. So each one of these individual items inside a set are called elements. And there's a key rule in sets. The key rule is that there are no duplicate elements. Uh, no duplicate elements. Okay? So this can't be a set. 1, 1, 2 cannot be a set because it has duplicate elements. If you want this to be a set, you would just write 1, 2. Okay, the elements can be finite or infinite. So we talk a lot about the set of all real numbers, right? Would this have finite elements or infinite elements? Guys, would the set of all real numbers have finite or infinite? Yeah, it would have infinite elements. So will the set of natural numbers or integers or rational numbers. Okay, so this is how you basically notate stuff. But what if you wanted to be a little bit more sophisticated? And that's where you use the bar method. Well, I call it the bar method. Okay, so we're going to define another set B, and then let's say, so the bar method is useful when you have certain conditions that you want, and you want to have the set of all things that satisfy your condition. So what I'm going to do is I'm going to write a variable. It can be anything. X is the most common. So here's the variable. And then what I'm going to do is I'm going to write a vertical bar. Sort of, right? A vertical bar, and then I'm going to write whatever condition I have. Let's say I want x to be a prime number. I'm going to write x is a prime number, and then close the curly bracket. So this would be your conditions. You might have multiple conditions, separate them by commas. And then here's your vertical bar. Yeah, so variable, bar, conditions on the variable. So what would this set look like, guys? It would be set of 2, 3, 5, 7, and then it would be an infinite set because there's an infinite number of prime numbers. Okay, how would you express 0 for this interval into a set? Do you guys have any ideas? How would you express this using the bar method?
X is greater than or equal to 0 and less than 4.
Oh, careful. The round brackets mean that there's no, yeah. So less than equal to 4. Yeah, you notate it like that. Okay. So that's a bar method. It's very commonly used, I think. Now let's see what we can do. Oh yeah, the funny enough, there's a set that has nothing in it, and that's very special. So we call it the empty set. An empty set is a set that literally has nothing in it. And we notate this by a very special symbol like that. So an empty set is a set that has nothing in it. Um, but here's a weird thing with sets. Sets can contain other sets. Okay. Sets can contain other sets. So I can have a set like 1, and then I can have a set of 4 and 6, and then I can have a set of, I don't know, 2 and 0,
What's
and
the
this
point
can
of
still
that?
be a set.
What's the point of that?
Well, it's more theoretical, right? If you, let's say, I want to set like x. X contains 0. I'm being sort of informal here. But if I wanted a set of all sets that contain the number 0, then it would be a set of what? It would be a set of integers. It would be the set of rational numbers. It would also be the set of real numbers, would be included in the set. And of course, there's an infinite number of sets that can contain 0. But my point is, sets can go into different sets, and that can change based on your definition. So a funny thing to note is that this and this are not the same. Can you see why? This is a set that's containing the empty set. This is an empty set that contains nothing. There is one element in the set. There are 0 elements in the set.
So there's a set
Yeah.
of nothing within the set, which makes it have something.
Yes. Yeah. That's the funny thing about set theory. I think historically, like, I think George Cantor, was the person who, like, progressed many of the rules that we see in set theory today. And there was like a huge argument about like, should certain sets contain other sets, and can a set contain itself without it being paradoxical? Like, you know, the barbershop paradox?
Oh, if the
If the
barber
barber
must
must
shave
shave everyone in town, like, but everyone in town cannot shave themselves, what does the barber do, right? So everyone cannot shave themselves, so they go to the barber. But if the barber has to shave himself, but like he can't shave himself. So that's actually something called the self-containment paradox, I think. If you have a set of all sets that do not contain themselves, then that set has to contain itself, but it can not also contain itself. So that was kind of like the paradox of sets. But they've improved the definition to exclude like those kinds of weird logic, I think. Yeah. So yeah, this goes like much deeper, but all we need to know for, the scope of high school and calculus is that we can arrange stuff like this. So there's a ton of operations that you can do with it. So I know I'm throwing a lot at you, but it's good to know these stuff. The most basic operation, I think, would be the number of elements operation. So n of A equals the number of elements in the set. Okay. So what would be the number of elements in this set?
3.
3, right? Because remember, this whole set is one element, and this whole set is one element when you look at the full big set, right? So this has 3 elements. Okay. So NA means the number of elements in the set A. Now, there's something called the union and the intersection. So a union has to occur between two sets. We call this, I think this is called the cup symbol. If you're trying to like type stuff in a computer, you have to type the word cup for this symbol to appear. So I'm calling it the cup symbol. This is called the union operator. It means all the elements included in A and all the elements have to be included in B. Oh yeah, I forgot. This symbol, I know there's a lot to sets, means includes. So X, this element, X is included in A. That's what this means, okay? And X is also has to be included in B for the union. So what does that mean? Oh, I'm sorry, guys. Sorry. I was lying. Or. Or, sorry. It's or. The union is or. So if I have the set A equals 1, 2, 3, and set B equals 2, 3, 6, then what would be the union of set A and set B? So we have to include everything that's included in A or anything that's included in B. And remember, sets cannot have duplicate elements to them. Sets cannot have duplicate elements to them, which means that what? 1, 2, 3, and 6 would be the union of A and B. Does that make sense?
Even the set can't have
Yeah.
the same number twice.
Yeah, it doesn't, right? So everything in A and everything in B, but they can't be duplicate, basically, right? Okay, the next basic operator is the intersection of set A and set B. So this is, I think this is called the cap symbol. And this is the intersection operator. So guys, we know about the intersection of two functions, right? If this is an intersection of the two functions, what does that mean? This point is on the first function, and it's also on the second function. So what it does, the intersection of A and B is defined as the set of all elements that are included in A, and it also has to be included in B. Okay? So in this example, what would be the intersection of A and B?
3.
Only 3?
2.
2. 2 and 3. They're both in A and they're both in B. So that would be the intersection of A and B. Okay. Next operation is called the difference operator. Okay. Complementary difference. Okay. We just have 2 more things to do. Set A minus set B, we call it that. So this is defined as all x that is included in set A but not included in set B. So not included, we just put a strike through through the included symbol. So this means not included. Okay. So basically, we remove any elements that are in B, but we still keep our keep the rest of the elements in set A. So what would be A minus B for our set A and B? So any element that is in A, but we have to remove all the elements that are in set B. What would be A minus B?
A minus B.
Yeah.
You only remove what overlaps?
Yeah, so you remove what overlaps with set B.
So just 1 and 6.
Well, you start with set A, right? You start with 1, 2, 3. You remove any overlaps with B. So you remove 2 and 3, right?
Yeah.
So the only thing you would have left in set A would be 1. Does that make sense? Yeah. Okay.
You wouldn't have 6 in there.
You won't have 6. No. You start with A and then you just take it out. You take out whatever is in set B. Okay. The final operator is what's called the complementary set. So we denote this by putting a little c kind of in the exponent position. Um, and this is the set. Oh yeah, in order to introduce the complementary set, I need to introduce you to the um, universal set. So the empty set is that. The universal set is the set of everything. Now, this might differ based on like what context that you're taking it. Usually um, for the universal set, you can think of it as anything that can happen within your situation. So if we're talking purely about real numbers, then the universal set would be every single real number. If you're talking about the possibilities of the outcome of a game, then the union set would represent every single possibility of that game. Okay, so the complementary set is anything that's included in the universal set and anything that is not included in set A. So anything outside of set A would be A complementary. I hope that those of you watching online can see that. Okay, so what we like to do with sets is we like to draw Venn diagrams. I think that's a really great way to visualize what's going on here. So in a Venn diagram, you would label the universal set that contains everything. You would have set A that's included in the universal set. This is called a subset. Oh yeah, final thing. I ran out of space. Subset. A subset A is a subset of B. We call it that. So you notice that there's no like third line in here. So this is when you're comparing an element to a set. This is when you're comparing a set to another set. So what does A included in B mean? It means that if, okay, for all elements that are included in A, that element is included in B, means. So A is a subset. If we're doing it in a Venn diagram style, then B would be the bigger circle and A would be contained inside of that. Does that make sense? And then obviously, well, we have the equality. If A equals set B, if set A equals set B, then they must be exactly identical for all x for all x in A, x must be in B, and for all x in B, x must be in A. Equality means that all elements so I'm introducing a lot today, but you see this inverted A? You see this inverted A?
Yes.
That means for all. This means for all, every single possibility. This double arrow, you'll see a lot of these double arrows in the notes, means that this means if and only if. This is more logic than sets, but sets and logic are really, really related to each other, which means that if you read it this way, it's true, and if you read it that way, it's also true. For all elements in A, that element is in B. For all elements in B, it has to be in A. So it's kind of like a back and forth thing. But I think without all this like jargon, you would, set A and B are equal to each other, they must have exactly the same elements. Okay, did I cover enough? I think so, right? Yeah. So as a final practice, if I had to fill in A union B, what would I fill in? Well, do I fill in everything? I fill in set A, and I also fill in this area, but would I fill in anything outside? No, right? Because this is the universal set. I write it in like sort of like a boxy style.
So if you would fill
Yeah,
in everything, it would be, sorry, it would be,
universal.
no, if you move it, is it behind you?
Yeah,
And
well, this is the complementary. So the complementary of A,
wouldn't it be
yeah,
fill in everything? You don't
would
know.
be everything outside of A.
But aren't those non-real numbers? Everything is all real numbers.
Oh, yeah. So the set of everything depends on like what context are you looking at, right? So it could be literally any context. It doesn't have to be numbers
But if
necessarily.
you're looking at
Yeah,
the outcome of something,
yeah.
then the complementary set would include outcomes that aren't even possible.
Um, no, because the universal set is the set of all possible outcomes. You don't really define outcomes that won't be possible. You won't do that, right?
No.
So you would define the set U as the set of all possible outcomes. If I was rolling a dice, the universal set would be the set of all possible outcomes of that dice. Okay? Yeah.
Then what would the complementary set be?
If set A is a roll that is even, and this is all possible rolls, and let's say set B is rolls that are multiples of 3.
It depends what you're looking at.
Yeah, it depends on what you're looking at. Then A intersection B would be 6, right? A roll that is even and is also a multiple of 3 that's only possible when the roll is 6. A roll that is even would have 2, 4, right? And then rolls with a multiple of 3 would have 6 and 3. And anything outside that, 1 and 5, would still be in the universal set, but it would not be in set A nor set B, okay? So a Venn diagram, especially when you're dealing with like probabilities or something like that later on, that's also very helpful. So yeah, that's all the theory we're going to do for today. How many minutes do we have left? We have about 10 minutes. So number one, can you turn to your notebook, workbook, guys? Thanks for listening. But with this continuity unit, I really wanted you to understand some of the more abstract stuff that math has to offer, right? The concept of sets I think it's very abstract. Like if we want to study this further, we would have to study like set theory in university. Number one, I encourage you to solve it yourself, right? Can we see what happens in number one? So we are given intervals, we are given sets, bar notation, number of elements. So it's everything that we've learned. So set A is all A that satisfies limit x goes to A minus is not equal to limit x goes to A plus. And you have to count the number of elements in set A and the number of elements in set B as well. So I think you can solve that on your own. And let's go to number 2. For function f of x and g of x, select all statements that are true. So I'm going to erase this. Is that okay? This side? Yeah. Okay. Number 2. So what kind of graph do we have here? Uh, f of x is like that. And it's close, open, open, closed. Okay. Closed, open, open, closed. And this is what? -1, 1, -1, and 1. So this is f of x. And what's our g of x? It's parabola, closed, open, closed. Okay, so -1 comma -1, closed, parabola goes up to 1, and then it goes down to -1, open, and then close at 1 comma 1. Okay, so this is our g of x. What does it tell us to do? Limit x goes to 1 of f of x g of x equals -1. So that's our first statement that we need to check. What do you think, guys? Is that true? Statement number A.
Is that multiplied by g of x?
Yeah, if you see nothing, it's multiplying, right?
If x goes to 1 equals -1.
So remember, the three conditions for a limit to exist are what? We need to compare 1 minus, 1, and 1 plus. Throughout this chapter, I encourage you to organize your calculations like this. So 1 minus would be what? So we go to 1 minus of f of x. Remember that we can split these apart as long as they are not indeterminate. So 1 minus, we go to what? 1, right? And then g of x, we go to 1 minus, we go down to -1. So that's -1. The function value, we also have to consider that too, right? Do we? Oh, not yet, not yet, not for A. So let's go to 1 plus. 1 plus, we go to -1, and then here we go to what? We go to 1. So -1 times 1 equals -1. So do these two values equal each other? Yes. So A is correct. Number B, function f of x plus g of x is continuous at x equals 1. Okay, so 1 minus of f of x and g of x. So here's how we might organize it, right? If you want to organize this, we go, yeah, okay, yeah. We go 1 minus 1 and 1 plus. We can write, hey, what's the value of f? What's the value of g? And what's the value of f plus g? Sort of like a mini table. Okay, so what's the value of f at 1 minus? Oh, the limit, sorry. The limit 1 minus f of x goes to 1. And then the limit at 1 plus, it goes to -1. And the actual value is what? It's at -1, right? And then how about g? 1 minus -1. At 1, -1. 1 plus, it's still -1. Wait. Oh, x equals 1. Sorry. X equals 1. 1 minus is -1. 1 is 1, and 1 plus is 1. And then we can simply add them. 0, 0, and 0. So they all exist, and they all equal each other, right? That means the limit equals the function value, so we can say that, yes, it is continuous. Finally, f of x times g of x. So we can add on to our table f times g. What's 1 times -1? -1, right? Because 1 times -1. How about the function value? 1 times -1 times 1, that's -1. And at 1 plus, it's what? -1 times 1, so that's also -1, right? At 1 plus, it's -1 times 1, so that's also -1. Do they all equal each other and exist? Yeah, right? -1, -1, -1, they all equal each other and exist, so C is also true. Right. Oh, wait. Wait, it's at -1. Oh, okay. Never mind. Sorry, guys. I should read -1 and 1 better. We compare the function values at here. So when we're multiplying, 1 minus, 1 and 1 plus, right? We're looking at -1. So we're looking at what? 1 times -1, and that's -1. The function value is 1 times -1, which is also -1. And then the plus value is what? -1 times -1. So that's 1. So they don't all equal to each other. So that means that the function f of x times g of x is not continuous at x equals -1. That's smart. But who knows? Who knows the mind of the person who created this question?
It's worth checking.
Yeah, it is definitely worth checking. Okay. Ooh. Next time we'll go over some more complicated stuff. So remember that we talked about the limit of a composite function, right? That was one of the more harder topics. Next time we'll talk about the limit, the continuity of composite functions, and we'll go on from there. I need to give you homework, right? Homework. So question number 1, and let's see. We did number 2. What should we do? I'll do number 3. I'll leave it as a challenge, okay? See if you can. Number 3 involves composite functions, so I'll leave that as a challenge. Number 4 and number 5, you guys can do. Remember, all the stuff that we learned in the limits chapter still will apply. Number 6. Okay. You know what? We'll do number 6 and number. I'll give you number 7 as a challenge as well. Okay. Okay. I think this is all that you guys can work on until the next class. So next class is on Monday, right? Yeah. Okay. All right. I'll see you guys then. Great work today for trying to digest all of the concepts that we did. All right. I'll see you on Monday, guys. Bye bye.